Hello, everyone. This is part 5 of my Chapter 6 notes. I'm going to talk today about conservative and non-conservative forces, and I refer you to page 14 of your note packet. So when I talk about conservative forces, I'm not referring to forces that, love Ronald Reagan and listen to Rush Limbaugh and, shop at Walmart. And when I talk about non-conservative forces, I'm not talking about forces that, listen to NPR and shop at Whole Foods. What exactly is it that we mean by conservative and non-conservative forces? Well, I'd like to illustrate conservative and non-conservative forces by sharing a series of scenarios. And as they say on Sesame Street, two of these things belong together, and one of these things just doesn't belong here. Now it's time to play our game. When a ball is going upward in scenario 1, the gravity is doing negative work on the ball, causing it to slow down. That's scenario 1. Scenario 2, when a box is sliding across a desk, friction is doing negative work on the box, which causes it to slow down. And third, when a sliding box runs into a spring, the spring exerts a force opposite the direction of the box's motion, causing the box to slow down. So what are the similarities between scenarios 1 and 3? Scenarios 1 and 3 are examples of conservative forces in action. And what that means is that the work that is being done to slow something down or bring it to a stop, in a sense, is being used to store energy that can later be recovered. So even though I might have a ball or some object which is flying through the air, and then it's being brought to a stop by gravity, the gravity can then do work on the object and cause it to fall, ultimately with exactly the same speed if you neglect friction. So without friction, you throw the ball up, gravity pulls it, gravity stops it, but eventually you can recover all of the velocity that you put into it when you threw that ball upwards. Similarly, if you have a box that's running into a spring or a mass that's running into a spring, the spring compresses, it stores that energy, and then it can go sproing and release that energy right back with no loss of energy, again, assuming that it's a perfect spring and we're neglecting friction. But we can't usually neglect friction. The world's not perfect like that. Can you recover in some way the work that the friction is doing? And the answer to that is no. Friction is just kind of taking things away or taking energy away from your box, and friction can't put that energy back into the box once it's taken out. Of course, energy is still conserved. The energy that is being taken away as a result of the action of friction has to go somewhere, and where that goes is heat. And then that heat then dissipates, and it's not of any particular use to anybody anymore. So that is an illustration of a conservative force, or two types of conservative forces, namely gravity and springs, where you can recover the work that those forces are doing, as opposed to a non-conservative force, which is friction acting on something where you can't recover that work later or put it back into the box, as it were. So negative work done by conservative forces can be recovered, in a sense, whereas negative work done by non-conservative forces cannot be recovered. If we're taking a look at the work done by a gravitational force, and if we're using the dot product definition of work, where work is equal to F, the vector F dotted with the vector S, and S in this case is displacement in only the y direction or with the y coordinate, and if we say that the direction of the force is 0 in x and mg in y, and that makes sense, if we're looking at just throwing a ball straight up, we find that the work is equal to mgy, which you may recall was the potential energy of gravity way back in part 2, I think it was part 2 of this video series. Similarly, work done by an elastic force, we have F dotted with S, where S is just in the x direction. It has only an x coordinate. And the force is negative kx, again, acting only in that x direction. Force in this case is a function of x, so we can't just simply neglect that. We have to take an integral. So the work being done on the mass in this case is the force vector, or the force vector dotted with dx, and in this case we're going from the initial position, which is x, down to a displacement of 0. So it's actually the lower bound is x, the upper bound is 0. And because f equals negative kx, we can pop this negative in front of this integral. We make the substitution kx. So we have negative integral over the interval from x to 0 of kx times dx. And remember, this is asking us to determine the work done on the mass when it is pulled by a spring with a spring constant k from a displacement of x to a displacement of 0. So again, those are our limits of integration. Is x being the lower limit of integration, 0 being the upper limit of integration. And therefore what we find is that it is 0 minus negative 1/2 kx squared. And so the potential energy of this spring is 1/2 kx squared. So that is the expression for potential energy in a spring, which again we saw when we were talking about potential energy in gravity. So the work done by a gravitational force and the work done by an elastic force becomes the potential energy of either gravity or the elastic force, respectively. Again, the negative work done by conservative forces can be recovered. Conservative forces also have another property which is known as path independence. So let's take an example of gravity. So we know that work done by gravity is negative mgh, and let's say that we have a ball here on some sort of flat surface, and we have a ledge, which we are calling h in this particular case. The amount of work that gravity does on this ball does not depend on the path that the ball takes from this lower ledge to this upper ledge. If we move the ball directly, or if we move it by some sort of crazy path, the amount of work done by gravity is the same, and the potential energy of gravity is the same as a result of that movement. So this is what we mean by path independence. It doesn't matter if that path is straight or if it's really crazy. All that matters is the initial position and the final position. However, if you have a non-conservative force, such as gravity, the work done by friction is path dependent. So if we have a ball over here, and that ball is moving from the left part of the screen to the right part of the screen, the least work done by friction is when you have a straight line path between this initial position and this final position. If we have some kind of crazy path or some kind of more complicated path, the work done by friction on this object is going to be greater than if it is just moving in a straight line. So this is what we mean by path dependence, and that's something which is seen in non-conservative forces. So that concludes Chapter 6. I hope you enjoyed the lectures, and I will see you next time when we start exploring Chapter 7. Take care, and I'll see you next time.